is on. All right. So this is what we got to do first. And by the way, when you're studying for the next test, you're studying for the quarterly, you should be looking at the objectives. That's what Cambridge can ask. When they develop their questions, they develop them off of the objectives. So if it said define electronegativity as an objective, guess what you were supposed to do? Memorize the definition of electronegativity. All right, so candidates should be able to define, underline your keywords, the unified atomic mass unit. That means they could say, define the atomic mass unit or the unified atomic mass unit. And this is actually something that I do go over in previous chemistry, but you probably forgot because it's like way at the beginning of the class. It's 1/12 the mass of a carbon-12 atom. Does anybody remember why we use that as the atomic mass unit and what in the world is an atomic mass unit? Atomic mass unit is AMU. Why do we use that instead of grams for atoms? Go ahead. Or too tiny, actually. If we were to measure the mass of an atom in grams, it would be something, right, like 10 to the negative 28th or something. And nobody likes to speak like that, like not even scientists typically. So we developed this scale called the AMU, and basically all you would have to do is count your protons and your neutrons to figure out the mass, and we called that the mass unit. Luckily for us, we've got this beautiful linking idea called moles. And moles links the mass of a single atom to the mass of a group of atoms, and you can still use the periodic table. All right, so go ahead and go to that. All right, so first thing, definition. Define means memorize, word for word. So you should be, when you study and you're studying for the next test, make yourself a revision guide, study word for word what the definition is. Typically, they tell you the definitions in the syllabus. Like it usually follows, define what it is. Define, relative atomic mass. This is a new script you're going to see, A sub R. Relative atomic mass, we really just think of it as like the molar mass. So when I think of the mass of an atom, and for example, zirconium, if I go to zirconium and I think the mass of an atom versus the mass of a mole of atoms, the mass of an atom of or the mass of a sample of zirconium is going to average out to be 91.2. That's an average of all the zirconiums I have on planet Earth will average out to be 91.2 AMU. If I have a mole of zirconium on planet Earth, it would be 91.2 what units? What grams? Because it would then be defined as the molar mass at that point. And so you're going to define the relative atomic mass, the relative isotopic mass, the relative molecular mass. Oh, these are actually all the same definition. Relative atomic mass, relative isotopic mass, relative molecular mass, and relative formula mass. What's the difference? It's a relative mass. What's the difference here? Atom, isotope, probably circle those words. Molecular formula. What do you think is the difference? It's literally all the same definition. You'll see that momentarily. Relative atomic mass, relative isotopic mass, relative molecular mass, relative formula mass. Look at those words. We'll come back to it. The words that make each of those definitions different. Because you should study what's similar. There's only one word different in all those definitions. They're almost all exactly the same definition. The next objective. Define and use the term mole in terms of the Avogadro's constant. Do you remember what that constant is? Yes. Positive 23rd. Because if you say negative 23rd, you're saying that there's 0.0000006 atoms. You can't say that because there's got to be at least one atom. So it's a positive 23rd. So define and use the term mole in terms of, this is the amount of particles in a mole, right? This is the amount of whatever in 1 mole of what it is. So if I said I define a mole as 6.02 times 10 to the 23rd particles, that's it. What a mole is. It's just an amount that we group together. Much like a dozen is 12, a mole, except for a baker's dozen, which Panera offers, a regular dozen is 12. A mole is 6.02 times 10 to the 23rd. Whenever we think of a mole, that's how much we have. That's the amount that we have. Calculate. Hey, we broke out the calculators, right? Calculate the relative atomic mass of an element given the relative abundances of its isotopes or its mass spectrum. This is actually something we've done in pre-ACE. You may not remember it right now, but when you see the process, you'll probably be like, oh yeah, we did that. And then finally, perform calculations, including use of the mole concept. Today we're at least going to be going in between grams and moles. How do we transfer grams to moles? How do we transfer moles to grams? We won't be doing full stoichiometry today. Like I said, it's an intro lesson. Notice, we're going to go over significant figures and metric system calculations. That's not even in here. Why isn't that in here? Because they assume that you already know it. There are some topics that are assumed that you know from prior classes that I go over anyways, just to make sure we're good here. And so you'll see me go over a little bit more than what's in here, just because it's a review of some things we need to know as we go forward. So here we go. Next slide. Rehearsed definitions. Take a look at what you got to memorize. And I know that it looks like a lot, but it's not as much as it looks like it is. The first one is the atomic mass unit. You've got to memorize that. The atomic mass unit, the unified atomic mass unit, is 1/12 the mass of carbon-12. 1/12 of 12 is 1. So basically the point of using that is to say that every proton and every neutron adds up as 1. So if I have an atom that has 12 protons and 12 neutrons, it would add up to a mass of 24. If I had an atom that has 1 proton and 2 neutrons, it would add up to a mass of 3. And so that's why we base it off of carbon-12, because it has an equal amount of protons and neutrons. Yes?
You said it's 1/12 carbon, right?
1/12 of carbon-12.
Is that like the new thing they used to calculate it? They used to have like, for the weight.
They used to do oxygen
Oxygen.
in the 1800s, and they changed it to carbon later on.
So it's based on the mass of carbon,
Mhm.
the weight?
All masses are based off of and relative to the mass of carbon. So all masses on the periodic table. What? This is so plentiful. It's the basis of pretty much all our
And
existence
it's,
that we
it doesn't,
know.
just like we did.
And it exists in the solid phase, so it's easy
Just like
to
we did
measure.
last class, it can be giant, and they could do silicon, but it's not observable as carbon.
Right. So what about these other definitions? The relative atomic mass. I would memorize relative atomic mass and then change one word for all the others. So relative atomic mass. The words you gotta get weighted average. So the relative atomic mass is the weighted average of a mass of atoms compared to the atomic mass unit, compared to the unified atomic mass unit. And so the parts that I've underlined and circled are the parts you need to get in there. This is usually a 2-mark definition. This is the word you replace. The relative atomic mass, which you're going to see as AR, for magnesium is 24.3. The relative atomic mass for potassium is 39.1. The relative atomic mass for hydrogen is 1.0. What is the relative atomic mass? We learned about it in pre-ACE. Yeah. You took it with me in pre-ACE. We went over it.
What was the question?
What is the atomic mass? Go ahead.
This is the average of all these.
That is the way that we learned it, right? It's the average of all the different versions of an element that exist on planet Earth. If we took all the different versions of an element that exist on planet Earth, all the isotopes, and we took all the percentages into account of how much we had of each, and we took the average of that, that's what the number on the periodic table is. So all we need is the weighted average. Is it's the average of all the isotopes, all the versions of the elements. So this is not the official Cambridge definition, this is just to understand. Versions of the elements that exist on planet Earth. On our planet. So, in a sample of whatever element you have a certain percentage of different isotopes. And so, for example, one that I remember off the top of my head that you'll actually need to know later this year is that 25% of all the chlorine on planet Earth is chlorine-37, and 75% of all the chlorine on planet Earth is chlorine-35. What does that mean? If 25% of all the chlorine is chlorine-37, and 75% of all the chlorine on planet Earth is chlorine-35, what do you think the average is closer to? This is something that I've asked in the past. It's closer to 35 because I have more isotopes that have a mass of 35 than have a mass of 37. So not only do you have to take into account the mass of your different elements, isotopes, you have to take into account how much you have of each. Taking into account how much you have of each is called a weighted average. So when we take the percentages into account, that's what we mean by a weighted average. Not a regular average. It's one where you have to take into account how much you have of each. And so this definition, I would just memorize word for word. And then when it says relative isotopic mass instead of atomic mass, I would switch out the word atom for isotope. If it says relative molecular mass, I would switch out the word atom for molecule. And if I see relative formula mass, I would actually switch out for the word formula unit, which you may definitely not remember. Notice, the definition is literally supposed to be exactly the same, so just memorize the first one, and then just switch out the word atom, isotope, molecule, formula unit. Atom, isotope, molecule, formula unit. Why would we describe something as a relative molecular mass, whereas another one will be a relative atomic mass? Like if I'm talking about magnesium, I'm going to say a relative atomic mass. But if I'm talking about methane, CH4, I would not say relative atomic mass. Why not?
Because it's more than one atom.
More than one atom. And so, yeah, so if I say that magnesium has an atomic mass of 24.3, that makes sense if it's a relative atomic mass. But for CH4, you would not say that the AR is 16 because it's not an atom. CH4 is a molecule. So you would not use AR, you would use MR, if that makes sense. And so all the wording here is to describe that this is for single elements. Molecules are for what type of compounds?
Two, like more than two elements.
Specifically covalent, non-metals. Only covalent can be molecules. And formula unit would be actually the word for ionic compounds because they exist in those weird cubic structures. That's why they're called formula units, yes.
So you would use MR for both molecular and formula unit?
Yeah, they do use MR for both. But I would say relative formula mass, I've never seen FR used in my life. I have only seen them use MR.
About for isotope.
It's kind of strange because, like, to me, I don't see too big of a difference here. But if they're talking about one of the isotopes, what it would be, the mass of a particular atom of an isotope. So just talking about carbon-12. Just talking about carbon.
Know about the MR.
Oh, well, it would be AR because it's just a single element at that point. So that would also be AR. So AR is what we use when we're talking about a single atom. MR is the terminology they're going to use, the little letter abbreviation they're going to use when we're talking about a compound of any type. And so this is a definition type question, recursive. Just like electronegativity, this is one you just got to memorize. Yes?
The R is a subscript. So it's not like argon.
Argon, no. It's not argon. So the R in the subscript stands for relative. Yeah. Relative atomic mass. That's what AR stands for. So not argon.
Yeah.
Not argon. The way I wrote it made it look a little bit, sorry about that. It is supposed to be in the subscript. All right, we're good so far? That was our first thing we need to know is just memorize this definition. So what about math? The math is actually usually where a lot of the marks are at here. And so how did we calculate the masses of the different samples of elements we find on planet Earth on the periodic table? How do we come up with those numbers? Well, we have a formula for that. And it's a formula you may be familiar with. They're actually able to determine this with a machine called a mass spectrometer. We're going to talk about mass spectrometer later on in this year when we get to organic chemistry because it's going to actually do more for us. But one of the things it can do is it can actually identify in a sample of an element. You put it through the machine and it tells you how much percent of that element is of each isotope. Like 99% is carbon-12, 0.1% is carbon-14, so on and so forth. There's a machine that you can literally run your sample of an element through it and it'll tell you the percentage of the element in that sample, the different isotopes. Yes? Because it can sense the masses when they hit.
Oh.
So what it does is it ionizes them, and then it senses the different masses when it hits like a detector. And so it's a complicated machine. They're expensive. FIU has one. I believe Miami-Dade does too. Like the colleges and universities in the area have these machines and other types of machines that do other types of identification. But we're actually going to spend later on this year spectrometry. We're actually going to be going over a few different types of spectrometry later this year. When we get to organic chemistry, we will revisit this topic. For now, all you gotta know is how to calculate masses. So the first way that we would calculate masses is actually with the periodic table. And so we learned this in pre-ACE called a molar mass. And it was one of the hopefully easiest things you did in the class. All you had to do, if given a chemical formula, is to find the average molecular mass. You would add up all the different atomic masses for each atom that you have. So if you have water, you have 2 hydrogens and 1 oxygen. Each hydrogen has a mass of 1, and each oxygen has a mass of 16. So you would basically put all that together and get that the total mass of water is 18. If I'm only talking about one water, I would say that this is in AMU. If I'm talking about 1 mole of water, what would I say? It would be 18 grams. We can measure grams. We can't measure AMU. Like in a lab, we have the ability with our scales to measure grams. So we will always measure for an amount of moles, which is that large amount. This is our periodic table, the one that we're going to be working with this year, the same one that you've been using. These numbers right here are the ARs. And it says it on the key for your periodic table that Cambridge gives you on the exam. It says relative atomic mass is the bottom number. So you're given that for every element on the periodic table. So before we move forward, use the periodic table to calculate the relative formula masses for each of the following. Calcium chloride. How would we do that? Ca and Cl2. By the way, if you didn't know, if you see what looks like a carbon and the capital I, that is not a capital I, that is a lowercase L, that is always chlorine. Yeah.
So that's part we just use the
Numbers on the periodic table.
yeah, but like we're talking about the relative one. For example, for potassium, we just use
39.1. Use the periodic table Cambridge gives you. Yes. So calcium, what will we do? What's the process? Do you remember? Take the amount of each element and multiply by the atomic mass on the periodic table. So if I have 1 calcium and each calcium has a relative atomic mass based off of carbon of 40.1, then I will use that. Chlorine, how many do I have? 2 times 35.5. And so when you are doing your rounding, oh yeah, significant figures are going to come into play later on. But you would basically just use the same amount of decimal places that your periodic table gives you. So if your periodic table from Cambridge goes to 1 decimal place, then all of your answers should be to 1 decimal place. So your answer here would be 111.1. And because we're just looking for relative formula mass, our correct unit here would be AM.
Yeah.
Copper to sulfate. About that one. 58.9. That's nickel.
Oh, that's-
63.5.
I'm in 60.
63.5. Sulfur,
159.6.
correct. And oxygen is 4 times 16. So when I had taught this in the past, I had you write out a chart like this where you list out how many you have in each element and you multiply by the number on the periodic table. Do you have to do that for Cambridge? No. They expect you can plug numbers in a calculator and come up with 159.6. They assume that you can do this. So 64, you add these numbers up. You said it was 159.6. That's the number I remember in my head as well. So did 159.6. Does this process ring a bell?
They don't give you a calculator.
You need a I would say yes, use a calculator. I would say you don't have to write all these steps down. Like what you see me doing here, you don't have to do that because it's implied that you know how to do this. Yes,
So on like math questions in the county exam, there's no like method marks. It's just
there are method marks, but this is not enough credit for a single method mark because it's too easy, is what I'm trying to tell you. I'll let you know where the method marks are when we get to the actual questions, but this would be something that's like not even like you have to do the step, but they're assumed. Right, they're like, you can type that in a calculator. When you do the dimensional analysis, like canceling out the grams and the moles, that would be where your steps are. Your steps are not in determining a molar mass. Unless they ask you to determine a molar mass. But that would never be worth more than 1 mark on a paper 2, and you'd be blessed or lucky to get a mark on a paper 2 where they ask you for a molar mass. I've seen it happen every once in a while, but super rare. And it's always for an organic thing. So it's like a bunch of different carbons and hydrogens and oxygens. All right, here we go. Continue. Notice it says check up 1C and 1D. That means these questions are from where? Where am I pulling these questions from? The Cambridge textbook, the Cambridge University Press textbook, which is a really good textbook. But it means these are not actually Cambridge exam questions. These are made by the makers of the textbook. And notice this actually was chapter 1. There is a world in which this would be the first chapter taught. The scheme of work from Cambridge does not suggest teaching this first, and I agree with that completely. If you start the year off with moles, everybody just cries. And we don't, not to say that it's hard, it's just that it's much nicer to start off with electron configurations than to start off with moles as your first topic for the year. Returning back from summer, hit them with the moles. That's how it used to be. They changed their chapters around a little bit, but that's why it says 1, because this was chapter 1. In the scheme of work, this is not the first topic, though.
132.1.
For the next one, you got that? All right, let's check it out. So, what happens if you got a polyatomic ion? What do? We have to consider how many we have, right? So, how many nitrogens do we have?
1.
We have 2. Because this 2 distributes.
I see.
It's just like math. That distributes. We've got 2 nitrogen times its mass is 14. We've got hydrogen is 8 times 1. Sulfur is 1 times 32.1. And oxygen is 4 times 16. So you get 64, 32.1, 8, and 28. Add all of that up together. And what do we get? Give me my calculator. 132.1. AMU. All right. The part B is the only part that's weird.
356.3.
I'll check it. That might be totally. You did the part at the bottom. You did what it said at the bottom. All right. This last one's weird. I don't think I taught hydrates last year, but you'll correct me if I'm wrong. This is actually something that's going to show up in the notes real shortly. If you see this 6H2O, this means that 6 water molecules are attached to the ionic compound. water molecules will surround them. Some actually stay hydrated and they form these beautiful crystals. Yes. Yeah, go ahead. Let me make sure my hall pass is that. Yes, you're good. And they're called hydrates. This is a hydrate, an example of a hydrate. So the way you understand it when you're doing molar mass, which is all we're doing right now, is when you see this is not a multiplication. You don't multiply by 6 waters. This means 6 waters are attached. This means hydrate, that it's hydrated with water. So you might want to make that note there.
Yeah,
I
'cause it's still
still
the same, right?
got the same thing.
Yeah.
Have to edit?
The operation is to do the molar mass of magnesium nitrate, or the atomic mass of or molecular mass of magnesium nitrate, and then add the MR for the waters. That's the idea. That's what it says to do down here.
The calculator can do both at the same time.
Yeah. As long as you don't multiply the answers here. Make sure you add them. That's what the note that I put here. If you have a hydrate, my suggestion is to calculate the mass of magnesium nitrate, to calculate the mass of the 6 waters, and then to add those 2 amounts together. And so for the magnesium nitrate, what do we get for that? And I'm just writing this out just to show you the steps, but you can literally just enter this in your calculator. You get the right answer, as long as you don't punch in any numbers wrong. How many oxygens should be in magnesium nitrate? 6. 6 times 16 is 96. So the mass of all the elements for magnesium nitrate is 148.3. I actually just memorized the mass of water because it's one you see so often. What's the molar mass? What's the molar mass of water? 16 for oxygen, but water itself is 18. So I'm just gonna show it here. It's 2 times 1, right? And then oxygen is 1 times 16. But you see water so often that it's like, but then I don't have 1 water. I actually have 6. So you take the 18 and multiply it by 6. That's all you have to do for that. Or you could just distribute the 6 and have 12 hydrogens and 6 oxygens. It'll work out the same. Just make sure you consider the fact that there's 6 of them. 6 times 18 is 108. So the mass of my magnesium nitrate is 148.3. The mass of my water is 108. Add 2 together, and you get what? I get 256.3. Hakeem, is that what you got earlier?
Yes.
You got the process. And this would be in AMU because we haven't gotten the moles yet. So the only thing tricky here is if you're given a hydrate. I want to give you a hydrate lab actually in the near future. I was actually thinking about Tuesday, but Tuesday's going to be virtually impossible because of the thing that's now happening on Tuesday. So potentially next Thursday. Test of the PSAT online system that we have to leave this room for somewhere between 30 minutes and an hour. So it is what it is. All right, so I just wanted to bring up what hydrates are here. Hydrates, this is something that is in the Cambridge Standards that you do need to be aware of. This terminology is important. Some compounds, whenever you see an ionic compound as a crystal, I don't know if you can get in your head what a crystal looks like, but it's kind of like, it's got like a clear, translucent component to it. Whereas some compounds look just like powders, others look like crystals. If there's a crystal, it's likely that there's water actually stuck into that crystal. And so we call that a hydrated compound. And one of the ones that exists that's very easy to secure, I've got a few. One of them is copper sulfate, and it's blue crystals. And another one is magnesium sulfate, which is Epsom salt. I don't know if you've ever soaked your feet in Epsom salt before, but that is a hydrate, yes.
Copper sulfate, the little.
That's the blue crystals, yes. The blue crystals, we've worked with them before. That's actually a hydrate. It's an example of a hydrate. And so whenever you see, and you are going to see compounds in lab where you're going to see these crystals, that means you likely have a hydrated compound, that there's water stuck in that compound. And one that doesn't have water in it's called anhydrous. So what is anhydrous? Break down that word. Hydrous means water, what does "and" mean? Like, think of antonym. Not water. Not hydrated. So when you see something that's anhydrous, that means not hydrated. So if you see more like a powder, that's anhydrous. I'll check when you guys have a question. I'll look at my chemicals when you guys have a question to do later on. Pull out some hydrates. I have some in the other room, but I think I have some in here. All right. Now, the next topic is how do we, from the percentages of each isotope on planet Earth, how do we figure out what are these numbers? What is the average atomic mass? And so this is a formula that you may be familiar with once you see it. What you're supposed to do in order to find the relative atomic mass for any element, if you're given the percentage of each isotope you have of it found on planet Earth, is you take the mass of each of your isotopes and you multiply by what's called its relative abundance. Then you have to change that percentage to a decimal by dividing by 100. So the reason why you divide by 100 is change from percent form to decimal form. After you have done this for each of your isotopes, you add your answers together, and this gives you the relative atomic mass. Let's go back to the example I brought up earlier. Very, very simple example, just to show how we saw this in pre-A's. I have chlorine 35. I have 75% of all the chlorine on planet Earth is chlorine 35. And these are rounded numbers. I have chlorine 37. 25% of all my chlorine on Earth is chlorine 37. How could I, from this formula and using this information, the mass and the percentage, which we also call the relative abundance, how could I figure out what is the relative atomic mass of chlorine? What is the AR for Cl? Let's see if we can apply the formula. What would we do? First, start with the mass, though. The mass of your first isotope of chlorine is 35. Then you multiply by
26.25.
75 over 100. Then the idea is you do this for each of your isotopes. So it makes sense you add. Then you go to your next isotope, isotope 2. Your next isotope has what mass? 37. And then you multiply by 25 over 100. I only gave you 2 isotopes, so you only do this process twice. If you had 4 isotopes, you would do this process 4 times. Go ahead and work this out in your calculator and see what you get. You should get something very close, not exact because I rounded, but very close to the average atomic mass on the periodic table. What do you get?
35.5.
And now look at chlorine on your periodic table. What's the relative atomic mass on your Cambridge periodic table? And that's how it comes about. For chlorine, yeah. Do you need to memorize that? No. For chlorine and bromine, actually later in the year, at the end of the year, you have to for another reason. So if you want to memorize it now, you can, but you don't have to at this moment. You don't have to memorize these percentages for chlorine right now, but I'm saying that there's actually a standard, like at the end of the year in organic chemistry, where you actually do have to memorize the percentage abundance for just the elements chlorine and bromine. So if you want to memorize it, you can, but what you do have to memorize is the process. Now, the process is you add up all of your information for your isotopes together. So it's all the information for isotope 1 plus all the information for isotope 2 plus all the information for isotope 3, etc., etc. And all of that always equals your relative atomic mass, which we also call the AR, just AR. Now, in pre-A's, questions I would give would be very, very simple, where I'd give you all the percentages, I'd give you all the masses, and I just ask you to add them up. At the ACE level, they may not always be so simple, so we're gonna take a look at some issues we could possibly have. The first thing I wanna bring up is, if I know that I only have 2 versions of chlorine that exist on planet Earth, and I'm given the percentage of one of them is 75%, and they don't give you the percentage of the other. Could you figure it out? So one of the concepts you've got to remember here is that all the percentages of your isotopes have to add up to 100, everything that you have. And so that's one of the little caveats that could be asked. We'll take a look at some other ones throughout this week and next week. All right, let's take a look. This is what paper?
Paper one.
Paper 1. So paper 1, let's see what it's asking us. This is how it's asked on paper 1. Sample of element X is analyzed using mass spectrometry. That's the machine that gives us a printout like this. It basically separates the different masses of the element, it detects it, and how much percentage of the particles are of each element. So this is a readout you get from a machine. And so you are told, and by the way, this right here, M/E, is called the mass to charge ratio. It's going to matter later on in this year. In a mass spectrometer, the charge is always +1. So it's always the mass divided by 1. So what is it then? Mass. So it's a very convoluted way of saying that's the mass. So I'm putting this here to help you understand the way that they're asking the question. This right here is the mass. 112, 113, 114, 115, 160. And this right here would be the percentage for your formula. So now that I've given you this information, you've got how many isotopes here? Can you see? 3 isotopes. You've got the mass of each one. You've got the percent of each one. Can you go ahead and do that calculation in your calculator now? Write it out if you need to, but see if you can do that calculation and come up with the answer. Yes. I'll go ahead and start writing out shortly, but if you want to beat me to the answer, I always highly encourage that. When I was in college, I would always work in advance with my professor to see if when they went over it, if I would get the same answer as they did. Yes. It's a good strategy when you're learning. I'm going to go over it shortly. I haven't worked it out yet. I'll tell you shortly. So, I'm going to go ahead and work it out now. It's an algorithm.
Divided by 100.
That number doesn't seem low.
It's also not on there.
That's a problem. Yes, Hakeem, you're right.
I don't know. I did all the math right. It's just calculator stuff.
Check to see if you get the answer. If you didn't get the answer, raise your hand so I can see what you put in your calculator. This is the work that I did in order to come up with the answer.
I got it wrong. On
Which-
the calculator.
I don't like that calculator. That's the worst calculator ever.
That's what I'm saying.
I don't know if you all remember my opinion about this specific calculator. It reads everything backwards. I'm like, please don't buy this one. There's a few of them left in this room for some reason, but it's like the worst. Use that one. It's just the worst. That's a good calculator. All right. Anybody who is unable to get the answer or needs help understanding this first question, please raise your hand and let me know. Yeah, because they rounded to the 10th place. So it's the same number, just rounded. Are we good here? Yes? Does this process ring a bell now that I brought it up? Is this something that you recognize from last year? Because that formula is the exact same one that we did back in previous chem. It's not any different. All right, we're going to take a look at a second example. This is paper 1. here's paper 2. So let's take a look at paper 2. And it is maybe a level 2 question. It's level 1.5. Remember, I like to sort questions into levels. Level 1 is the easiest it could possibly be. Level 2 is medium intensity. And level 3 is oof. And on a Cambridge exam, you're always going to have a variety of questions. You don't know which standards are going to be tested at the easy level. You don't know which standards are going to be tested at the medium level. And you don't know which standards are going to be tested at the oof level. So that's why it's really important you know everything, because that way you have an idea when they ask for the easy points, you can get the easy points. Yes,
For this question, I got 114.35. I just rounded
you
up,
round
right?
it. Yes. It's C.
Can we bring our calculators and take numbers?
That's a great question.
There you go.
So for the Cambridge exam at this school, well, first of all, internationally, you are allowed to use a scientific calculator for the Cambridge chemistry exam and all math and science exams. You're allowed to use a scientific calculator. It is not allowed to have a back. Meaning you have to remove the back off your calculator before you enter the exam room. If you have a back on your calculator during the exam, they can invalidate your test. Yeah, because they think you're cheating with the formula sheet. That you've written answers or something on the back of your calculator. Yes, that's the truth.
They have
That's the
inches to
regulation.
centimeters and kilometers.
Yeah, there's stuff on there.
What is the thing?
Anyways, the school has calculators they can lend you, but this is the ones that they have.
Those are the worst ones.
Also, we should take.
So I advise not using the one the school gives you. Bring your own. I have my own to lend out, but I don't have enough for like everyone. But if the morning comes of the Cambridge exam and you got to school and you forgot your great calculator, swing by my classroom before you take the test so you can borrow one and don't be using the awful calculator. What?
I don't know where mine went. I thought it was,
You might have left it somewhere. All right, so that's a great question. I'm going to continue now. So let's see if we can solve this question from paper 2. Notice the way that it's been given to you. They're trying to be slick because they think you're going to think that this answer is what? Just by looking at the numbers.
19.
If you did no work whatsoever, you would think the answer is 19 and it's not.
Oh.
But they're trying to be slick because they're like, oh yeah, they're going to think that the pattern, but the answer is not 19. They do that sometimes. There's some psychological mischief happening on Cambridge exams.
I don't know that.
About that.
Watch test taking strategies. Be careful. Don't just assume. Make sure you do the work. They're trying to trap you oftentimes. I know. I've seen a lot of questions. Let's take a look at how to solve. This time they give you the AR. And they are asking for you to solve for a missing mass number. So how should we go about this?
Well, they gave us the estimated value of neon, so just find the values
That lead up.
for 2 and 3 and then just subtract that from neon.
Absolutely. So some algebra is going on here. So the way we would go through this is our first mass we would call x. So this would be x times 9.25 divided by 100. So far following me? Then I would do 20 times 90.48 divided by 100. Then I would do 21 times 0.27 divided by 100. And then I equal that all to what? 20.2. Because they told us the relative atomic mass is 20.2. So this time, you're not solving for the final amount, you're solving for one of the masses. So in order to do this, you have to do some algebra. Is it? Put all of this together. Is it so hard or are you being sarcastic because you're in ace math? Are you okay with me combining all of this together into a number in the calculator, or do you want me to do each term separately?
We don't.
All right. I got 18 18.1527, check to see if you get the same. Cheating kind of stuff. Alright, I got the same thing twice. Sometimes I do it in the calculator twice just to make sure I get the same answer, to make sure I didn't punch anything in wrong. So I got these two combined to 18.1527. And then what's 9.25 divided by 100? Just put in your calculator. 0.0925x. Don't try to do stuff in your head. It's a Friday, you're tired, I get it. Maybe. Do we have this so far? Do we understand what I've done? No? Yes? I divided these two numbers, put an X. I combined these two terms to make this. And then this I just dropped out. Yes. How do I do it? I do 20 times 90.48. So just to show you what I put in my calculator, I put 20 multiplied by 90.48 divide by 100. That's the order that I write it in. I go top first and then divide. Because remember, the number on the bottom for this 20 is a 1. And the number on the bottom for the 21 is a 1. Right? So that's the way it works. Are you good with that? Yes? Okay. Now to solve for x, I have to subtract both sides by 18.1527. Yes, there's going to be numbers. I am so sorry, but we are in the numbers. It's just, they're decimal numbers. They're gross. 20.2 minus 18.1527 is 2.0473. Tell me if you understand that. 20.2 minus 18.1527 is 2.0473. Did you get that? Now how do I solve for x? I know, it's numbers. Oh yeah, I'm so sorry, 8th math students. You've got math after math for the next several weeks. All right, so this is x equals 22.1. But if I write that, I'm wrong.
X equals 20.
Right.
So you have to round it to among significant figures.
Well, it's not even that. X is 22.1. Are we okay with that so far? Why do I have to write my answer as 22? The answer is actually not because of significant figures. Because significant figures would have suggested, well, I guess significant figures could suggest it too. But there's another big reason. Why does this have to be a whole number? Mass number equal protons plus neutrons. Protons are whole numbers and neutrons are whole numbers. So because what they're asking for is a mass number, your mass has to be a whole number. And ha ha, it's not 19, it's 22 is the answer. All right, there's a method mark here, by the way. Someone mentioned method marks. This is your first time doing math in chemistry this year. So method marks basically are marks you can earn even if you don't get the correct answer, but you have the process. The method mark is for this formula right here. If you got that formula, but you were unable to do the algebra correctly, you get 1 out of 2. If you have no work shown, typically they will not give you the full marks for the question. You have to show your work. So this is my time to tell you. Make sure you're showing your work. For this question, the work required to be shown is right here. You have to at least show this, and then you can plug stuff in your calculator. You don't have to show, like I do, explicitly every single subtraction that you do, but you have to show what you put into the formula, like what you're solving for. That's what you have to show to get full credit. All right, so this is only her 2 marks. 1 mark for the method, and then 1 mark for the final answer being correct. 2 marks, that's not a lot actually. On a 60-mark paper, not a lot of marks. Would you say this is difficult?
No.
The level, I assorted it to 1.5, meaning that it's not the absolute easiest they could ask it, but it's really not that difficult for this concept. There are more difficult questions. I will leave them off today because it's a Friday, but next week we'll take a look at something that's a little bit more difficult. Friday, and not only a Friday, but like the end of the day Friday. All right. I believe we are getting close to our last topic. I don't know how many slides I have left, but well, we also have significant figures and unit conversions, so we got a little while to go. Mole. This is a definition in the objectives. Didn't they say defiance? So the amount of a substance which contains 6.02 times 10 to the 23rd specified particles. You've got to get Avogadro's number in there if you are defining a mole. So 1 mole is 6.02 times 10 to the 23rd particles. It is better to say particles than to say atoms, molecules, ions, or electrons, because when you say particles, you're just grouping them all together. I could be talking about any of them. I'm talking about just particles. I've got 6.02 times 10 to the 23rd particles. By the way, this month, October 23rd, is National Mole Day. National Chemistry Week starts October 23rd. I'm going to give Johandri some jokes to do over the speaker in the morning. So that's going to happen.
No, please don't.
He already said yes. It's going to happen. I'm going to make it happen.
What's the last one?
He had some good jokes. Yes.
The worst part is, really can't comprehend.
Is it?
Yeah.
Apologies, that's rough. But you know, you're actually not in a bad position. Like, quarterly hopefully won't hurt you.
I'll tell you.
You should still study because that's how you arrange your levels, like to kind of get an idea. So make sure you're studying the way you would for an end of year exam. Like, review everything. All right, mole and Avogadro's constant. Something you need to know. You can directly relate moles to grams using the periodic table. So 1 mole of Na equals 23.0 grams of Na. All you gotta do is look for the mass on the periodic table, and that tells you the amount of grams in 1 mole. So we know that in 1 mole of sodium, that big amount, 6.02 times 10 to the 23rd, we can measure that on a scale. We have scales, they measure grams, we can figure out, oh, that's how many I have for a particle. Funny thing here, the abbreviation for mole is MOL. This is the short version of the word mole. You took out the E. All they do is take out the E. So like when you do molar mass, so for sodium, the molar mass is grams per mole. It's like that. G over mole. MOL is the short for mole. They cut off 1 letter, just FYI. I don't know why. I didn't decide that. It's just the way it is. You can't do ML because that's milliliters. But like there's like letters for different things. Mo is molybdenum, depending on if you capitalize the M or not. All right, so something you've got to be able to do is interpret amounts. If I have a mole of NaCl, you've got to be able to read that correctly. 1 mole of NaCl has the following. 1 mole of sodium. You agree with that? 1 mole of chlorine. You agree with that? 6.02 times 10 to the 23rd. I actually am looking at this. Wouldn't it be sodium ion? I think that's ion. Because it's NaCl. Ions of sodium and ions of chlorine. That's ion. So better word there. 6, that's I don't even think I've ever noticed that before. But it is Na plus and Cl minus, right? So ions would be the better way to describe that. Now, what if I had CO2? 1 mole of CO2. How many moles of carbon would I have?
1,
How many moles of oxygen would I have?
2,
Right. And so you've got to check the numbers for each atom, for each element. That tells you how many of each element you have. That's one of the key ideas, concepts you've got to understand throughout this unit. So I've got calcium carbonate. I've got 1 calcium, 1 carbon, and 3 oxygen. All right, so that's some things just to know. Significant figures. Remember how we spent actually, because I did this here, 2 class periods, if you had pre-ACE with me, going over rules for significant figures. And everyone's like, that's gross, and I hate it. And so there's good news and bad news here. The bad news is they assume you know significant figures in this class. They assume you know these rules by heart. The good news is, generally speaking, Cambridge is actually not very harsh on significant figures, especially not at the AS level. They're usually like, hey, if you gave us 3 significant figures in your answer, you Gucci, you good. So there's bad news and good news. The bad news is they assume you know this already. It's not in the standards because they assume you know it. The good news is, if you're unsure where to round to 3 significant figures. So that's just a hint. If you're unsure where to round, if unsure, round to 3. There is a 90% chance you'll get it right. Yes.
Is that for all classes? Because Mr. Horowitz said the same thing.
I think it must be the Cambridge examiners in general. It must be a British thing. Because in America, we are so picky about significant figures. Like when I went to school, if your significant figures are wrong, they're like, oh, you're failing. Like it was like such a thing, such a big thing. But here, I mean, in the international curriculum, they're like, it's not a big deal. Anyways, these rules you got to remember. And I did give an assignment. 80% or higher you have to get on it to get full credit in the grade book. So here they are. When you're looking and evaluating a measurement, numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9 are always significant. The only question we're ever going to have is with the number 0. Zeros before a number are not significant. So if the 0 occurs before, I read it left to right, and the 0 is before the non-zero number, never significant. It is literally just there to hold the place of how small that number is. So far, so good? We probably would never even write a number like this out. We would write this in scientific notation, typically, which your calculator can do for you. You don't have to memorize how to do scientific notation. If you don't know how to put your calculator into scientific notation, come to tutoring, and I'll teach you how to do that. Tutoring is next week, Tuesday next. It's like quick shortcuts. After a decimal point, zeros after numbers are significant. So this right here has the 2 is significant, the 3 is significant, and the 0 on the right is significant because they wrote it for a reason. The 1 on the right. Zeros in between numbers like 305. If the 0 is in between 2 numbers, it's always significant as well. And this one is important though. I advise this. If you're performing a multi-step calculation, I highly advise to wait to round significant figures until you're done with your final calculation. If you round after every step, what happens is you round and then you round again and then you round again and then you round again. And for some processes, like empirical formulas, you may end up with a totally wrong answer as a result of doing all that rounding. So my high suggestion, rule number 5 here, in multi-step calculations, wait to round until the end. That means just hold the numbers in your calculator and continue. All right, next thing. Rules for adding, subtracting, multiplying, and dividing. Yes.
What if we had the number 30 Would that be one or two significant figures?
That would be two.
Oh boy. The truth. One. Wait. Two.
Oh.
Anybody remember that?
Is that the decimal?
Yeah, in order for the zero to be significant on the right of a non-zero number, there has to be a decimal. So just to answer your question, I'll write it at the top here. This would be two significant figures, and this is one significant figure.
Wait, but it does count, the zero does count after 0 point something, right? So 0.10 would be two.
Yeah, so if you've got 0.010 like this, that's still two. Because it's the same rule being applied. There's a decimal there, the zero on the right is significant. Yes.
Why would that be significant? Like the same number?
The truth is, and that's why I said Cambridge is not nearly as picky as general chemistry is. And so the truth is, we read this, chemists, we read this as approximately 30. If there's no decimal there, we don't read it as exactly 30. We say, oh, it's rounded to 30. It could be 27, 28, 29. So it's like me going to my bank account and I would tell you how much I have. I'm just going to put a random number. I go to my bank account and I don't look at my Wells Fargo account, but I say, okay, I think I have around $13,000 in my bank account. Then I look and I see if that's exactly right or not, but I round it to the nearest where? I most likely round it to the nearest 1,000. Whereas I go to my bank account, I see I have $12,795. Not exactly 13,000, but I was in the general vicinity. So if those zeros are at the end, they're assumed to be rounded. What?
Folders, sorry.
Yeah, the folders are over there. Anybody can pick up their folder. Do you get the difference? So we assume that if we have a zero and there's no decimal at the end, that it is a rounded number, that it is an approximate number. In order to say it is exactly 30, the decimal has to be there. And that communicates, I have measured exactly 30. I know this is exactly 30. I have exactly $30, whatever it is. So it is exactness that's different. Now, once again, is Cambridge very picky about this? Not really, and unfortunately, sometimes even in their questions, they won't put a decimal when they really should have. Which is why I said, if you get confused and you're unsure, how many significant figures should you write?
Three.
Three, just to be safe. And in the lab, they'll literally say in the paper 3, write your answers to 3 or 4 significant. Like it literally says it in paper 3. All right, so the next thing you need to know, adding and subtracting rules versus multiplying and dividing rules. The multiplying and dividing rules are the most important. Because of something called dimensional analysis. Remember that thing with top and bottom numbers? You had to multiply and divide and cancel stuff out. It's coming very soon. It's all multiplying and dividing. So when you're multiplying and dividing, you have to count significant figures, and you're supposed to round your answer to the lowest amount of significant figures. Good news, usually whatever number you're given is the amount of significant figures of your final answer. So you just have to count how many significant figures are in your initial values, and then you look for the smallest amount, and that's the amount that you should get in your answer. Take a look at these rules. The rules for multiplication and division are down here. 2.357 has how many significant figures?
4.
4. 10.343 has how many significant figures?
5.
Which number is smaller, 4 or 5 significant figures? So your final answer should have how many significant figures?
4.
That's the way to evaluate it. Your final answer should have 4 significant figures. Adding and subtracting is a little bit weirder. I go over a big explanation in Prius. I'm not doing that here. All you got to know is that you count the decimal places and you cut off at the lowest amount of decimal places. So 1.4 is how many decimal places? That's how many numbers after the decimal? 1. 0.33333 is how many decimal places? The lower amount between those two is? So your answer should only have 1 decimal place. That's the rule for adding and subtracting. You will not see that rule applied very often in this class. However, it technically should have already been applied in this lesson. I just hadn't taught it yet. Where in this lesson have we already added numbers?
When we were adding like the relative atomic mass.
even if you go back to here, right? You get a value here, you get a value here, and you get a value there, you're adding numbers together. So technically, you should be applying those rules. All right, so real quick, review of significant figures. Can you answer these questions? How many significant figures in A?
2.
2. How many significant figures in B? 4. How many significant figures in C?
1, 2.
2.
5.00.
Because the point makes sense.
The point makes them significant, yes. Go ahead. No. This is 5 times 100, right? Scientific notation does not change significant figures. Doesn't affect at all. You may want to write that down because a lot of times scientific notation does not affect significant figures. If you see times 10 to the second, you see times 10 to the billions, it doesn't matter. So if I see 3.85 times 10 to the negative 7, how many significant figures does this have?
3.
Because I just care about these numbers in front. So 3. We only write, yes. Question? You're okay with this? Move on. Next thing to review, metric conversion. So, you should just memorize the acronym because for Cambridge, you don't have to go anything smaller than milli and anything bigger than kilo. The acronym that should have been taught to you sometime in middle school most likely, and if you took the class with me, I taught it, was King Henry died unusually drinking chocolate milk, poor King Henry. And so in order to convert between different units in the metric system, you should write this down. Because all you have to do is move your decimal to the left or to the right. And so what you should do is identify where you're at and where you're going. And then use that to tell you where you're moving the decimal. So look at the first example. Where are you at? Where you go? Where's meter? Is that M or is that U? So this is centimeters. Centi is a prefix. This is meters. There is no prefix. One letter means you're in the base unit. So you may want to write that down. So we're going to? Where are we going?
2 meters. 2 units.
We're going to here.
Basically.
So what you'll see is you'll see me use a different color or something. So I'm saying this is where I'm starting. This is where I'm going. What do I now need to do?
Subtract 2.
Or move my decimal over 2 spots to get to my unit. I don't see a decimal there. Where is it?
It's behind the 8.
If it's a whole number, it's at the end of the whole number. So it's right here. Move your decimal over 4.38 meters. We recognize this strategy? All right, do the next one. DM to M. Where are we moving the decimal? How many spots?
Does it stand for the first year or second year?
That's a good question. This is deca, and this is deci. Literally, just so you're aware, Cambridge never uses deca or hecto. Like it is not used by Cambridge. So if you see D, it's gonna be deci. The prefix for D is actually, the first D is actually DA. Deca is actually DA if you were to see it. Instead of just the letter D. So it goes dad. D-A-D.
Okay.
So just D is deci. But I am telling you that I've never seen them test hecto or deci. I keep them here just because we need to go from unit unit to kilo, and we know we need to move 3 spots to get there. So decimeter to meter, how many spots, which direction?
One spot to the left. No.
1 spot to the left, right? I just write down King Henry died unusually drinking chocolate milk. I'm starting here, I'm ending here. 1 spot to the. So this would then be what?
0.02352.
When I change my units for metric conversion, do I change my amounts of significant figures?
No.
It's still the same measurement, right? So the significant figures at the beginning and the ending should be the
Same.
same. Are they?
Yeah. Yeah.
So that's not a point, doesn't that mean that?
The 0 to the left is not significant.
Because it's still left, never mind, I get it.
So it doesn't change significance. All right, kilograms to grams. Next one. Move left to right. How many times?
3 to the right.
3 to the right. 1, 2, 3. 34 to 34. Grams to milligrams. Move which direction? How many times? Grams to milligrams. 3 times to the right again. 34.2. So I expect you for metric conversions, and Cambridge does as well, to be able to convert these pretty much like that. You should be able to just like move your decimal over. You do not have to show dimensional analysis for this. This is by far the easiest way and the way you should go. Last one is the only one that's a little bit difficult. 32.55 centimeters cubed to decimeters cubed. Let's talk about this. What happens if your unit is cubed? You're in volume instead of length, right? So instead of moving over 1 time, pay careful attention to this. If you see it's cubed and you have to move over 1 time, you actually have to move over 3 times. So if it is cubed, centimeters cubed to decimeters cubed, every movement of 1 is actually a movement of 10 to the 3rd. You have to move over 3 times. That's something important here. So to go from 32.55 centimeters cubed to decimeters cubed, you move over 3 times to the which direction? Left. So it's 3 times. 1, 2, 3, because it's a volume. And so it's 0.03255. You're not going to see too much with this now, but when we get to ideal gas law later on this unit, this is going to be a big deal. Like you're going to have to know that. I'll bring it back up, obviously, when we needed to solve questions, but this is the only thing with metric system that can be confusing. If it's cubed, for every movement of 1, you move 3. If it was squared, for every movement of 1, how much would you move?
2.
The decimal. 2. Yes, Justin.
Today was different units, like you were doing kilograms and grams.
Yep.
And it was cubed.
Kilograms cubed to grams cubed, you would move over 9 times. If that was a unit that existed. Mass cubed. But if it was kiloliters to liters, yes, it would be that.
That was the one to do that.
Kiloliters to liters. That would make sense. All right, are we okay with this? Or kilometers to meters? It would make sense that way. Okay, so that's the next thing that isn't in the standards. Cambridge already assumes you know how to do this. They assume you know how to do significant figures. They assume you know how to do metric conversions. Of course, we go over it to make sure we're on the same page, but we're going to need it as we go into the math in this class. All right, so the next thing, we're close to the end of what we need to do for the day. This is where the content really starts. There is a formula to solve for moles. Moles is defined as the grams of whatever you have divided by what we call the molar mass. actually a formula you can use to solve for moles. If you hate dimensional analysis, you can use this formula to solve for moles. You take the grams, you divide by the molar mass. Some of you may remember I gave you all strategy. I was like, this is the way we should do it, but if you hate math, I was like, here's a triangle. I don't know if you remember that. I did that in most of the classes, if not all of them. And I was like, you could do this. Moles equal gram over molar mass. And so if I have the moles and I have the molar mass, I can always multiply them and come up with the grams. And if I have the grams and the moles, I divide them to get the molar mass. And if I have the grams and the molar mass, I divide them to get the moles. It's literally like a secret triangle. That will give you anything you need to solve the question if you hate algebra. But this is the actual formula. Moles equals grams over molar mass. I would memorize this because you could solve a whole lot of questions with this formula. Molar mass is defined as grams over moles. So literally all we're doing, for those of you who like math, is we're canceling out the grams. That's literally all that's happening, and moles equals moles. So then, let's take a look at the kind of questions we could get, and then I'm going to show you how to solve it with the formula, and then how to show it the traditional method. Here we go. Example of calculating moles. The traditional way of doing this would be to use what we call dimensional analysis. This is the question. How many moles of calcium chloride are present in 200 grams of calcium chloride? First step, find the molar mass. The molar mass is the MR in grams per mole. So the MR, which is the relative molecular mass, if I am doing this for a mole, it is called the molar mass. This literally means add up all the numbers from the periodic table. That's what the molar mass is. Then, what we would do traditionally is we would use molar mass as a conversion factor. You would start out with your given, and this would be called your conversion. You would put an invisible 1 under here, and then you would cancel out the grams, and do 200 divided by 111, and that would give you the answer. So I'm going to show this from scratch, obviously. Yes.
You round down from, because calcium is actually 40.1.
So it should be 111.1.
Okay.
That's should be 111.1. So how do we do this from scratch? Let's take a look. I'm going to show you the traditional method, and then I'm going to show you the method using the formula, and then you're going to choose which one you want to do. Okay? So use the AR values to calculate the amount of substance in moles in the following. So you've got 10.7 grams of sulfur, and they want to know how many moles is this? How many moles? Traditional method, how I taught it in pre-A's, how it would be taught in any American class, is to start with your given. What's your given? It's the number that's provided. Find the molar mass, which is the, in this case, atomic mass of sulfur. What's the molar mass of sulfur?
For 32.1.
So I'm writing, what does that mean? Grams per?
Mole.
So that means there's 32.1 grams in
1 mole.
1 mole. So that's how I had taught you to write it before. If you had a molar mass, that was the amount of grams in a mole. Then what we did, once we found the molar mass, is we would write out our given, 10.7 grams of sulfur. What number would I put on the bottom of that given?
32.1.
Maybe, yes, but right now I would just put the number 1, right? Then you were supposed to make a decision. You were supposed to decide how to use the molar mass. Do you multiply by 32.1 or do you divide by 32.1? Do you remember how to make that decision? You start with grams on the top, so the unit here on the bottom has to be,
Mole.
it has to match. It has to also be grams because you have to cancel out grams. You have to get rid of grams to get the moles. So we would divide by 32.1 on the bottom, and we would put 1 mole at the top. And so this would give us the math we have to do. The math we have to do is 10.7 multiplied by 1 divided by 32.1. Or just 10.7 divided by 32.1, which is? I can't do that in my head. Oh, it is 1/3. So how many significant figures? It's too late in the afternoon. So what is it? 0.33. Where do I cut it off?
That's 3 significant figures.
3 significant figures. You don't write 1/3 as an answer. You write 0.33, and that's of what? Alright. Now what's the alternative method? Alternative. I hate math. Alternative. You have the grams. You have the molar mass. If I take the grams and divide by the molar mass, I will always get the moles. Right? That's what this says. So the alternative method is just use the formula. Moles equals grams over MR. Grams is 10.7. MR is 32.1. And that is 0.333. It's exactly the same technique, just shown a different way. Yes. Question.
Will we put it all the same question?
Yep.
It's easier to do the alternative.
Absolutely. Yes, it is easier to do the alternative. I'm quite aware of that. That's why I said I advise you memorize that formula. So if you memorize this formula, you can get through all of these at least simple style questions quite quickly. Is this allowed to be used by Cambridge? Of course, because this is actually what they present in the text. Cambridge actually doesn't really use dimensional analysis. It's an American topic. So in America, we do this. This is how we do it in America. In British, we actually do that. The alternative is the number 1 for the British way. So just so you're aware. That might bring smiles to some faces because you're like, oh, the American way. But if you were to take a university chemistry class, it would look always like this. Every professor I've ever taken does it like that. So you need to be aware of its existence. All right, continue. Next one. Let's do the alternative this time, since you are now familiar with the alternative and the fact that Cambridge likes that better. So what do we do? What's the first step? What should I get before I do anything else?
Atomic something.
Get that molar mass, right? So I need the molar mass for FeNO3. Do I expect you to make a table or a chart for this? No. What you could do now that you've got the idea, iron 55.8, nitrogen 3 times 14, right? What's nitrogen?
42.
42. Oxygen 9 times 16. Check me, is that 140?
Yes.
And then add those together. Molar mass for FeNO3 is? I get 241.8. Is that what you get? You just gotta make sure when you plug your numbers in the calculator, you don't mess up. That's where it can go wrong. All right, step 1. Are we gonna use just the formula this time? So the formula is moles equal gram over MR, molar mass. So how many grams do we have?
60.2.
And our molar mass is?
241.8.
And that gives us? It's actually actually 1/4. But we've got calculators for that, so don't stress it. And if we really wanted to be accurate about our significant figures, what would we actually answer? If we wanted to be really accurate about our significant figures, how many significant figures are here? So our answer should actually have 4. So it would actually be 2.25, and the calculator doesn't give this to you. You would actually have to add on the zeros, because the calculator will never show zeros at the end. So you'd end up with 2 zeros. So just in case it shows up on your quizzes, if they ask you for accurate significant figures, you would add in here to get 4 significant. Does Cambridge really care? I told you they're not too picky on significant figures, but just in case. All right, are we good with this technique? Yes. How far do we have? Oh, okay. We should be good. So now 5. What about this though? What should I do here? What's going on? Is the value of the Avogadro constant to calculate the total number of atoms in 7.1 grams of chlorine atoms. What are we going to do? Times 7.1. What do you suggest? Yeah, so the strategy, I'm going to write out a strategy. Grams cannot go directly to atoms. We do not have a link between grams and atoms directly. But what we do know grams can go to is moles. And we know that happens with the molar mass because we just did that, right? Grams goes to moles with the molar mass. Then we also know that moles goes to particles. Atoms are a type of particle. And we've got a way to do that. We would use a number. 6.02 times 10 to the 23rd. It's a constant. A question you may have is, do you have to memorize it? I believe in Prius, I told you you needed to memorize it there. It's actually given on a data table in the Cambridge exam. Like, it's a provided number in a data table. So you technically don't have to memorize it, but I would just know it because it is used relatively often. So how are we going to do this? Now, how do we apply our strategy? So we decided, or at least that's what I heard from the group, that we like this better instead of using dimensional analysis, right? So grams is what?
7.1.
Molar mass of chlorine atoms are? What? So I was going to bring that up. I'm glad you are on the same page. It says here atoms. It's not the standard state. But if it said chlorine molecules, what would they be talking about? Now it's standard state. So the wording is something you should take note of. This was worded very specifically chlorine atoms, which means it's just the mass of one chlorine. However, if you were told chlorine molecule, it would actually have been Cl2. So the molar mass here is 35.5. The short story, 7.1 divided by 35.5. These numbers are all pretty easy to work with. You get 0.2. I'm not going to address significant figures till the end. So what's the next thing to do? This is my moles. What do we do next? How do we change moles to atoms? How do we change moles to atoms? You would technically, I'm going to use dimensional analysis, but you just got to recognize if there's 6.02 times 10 to the 23rd atoms in a mole, you would be multiplying. I'm going to show the dimensional analysis just to show this is the way it's supposed to work, but you should just take 0.2 and multiply. We're about
Good afternoon, Golden Lions. This is DeCarlos Garcia, and these are your afternoon announcements. Students, please remember to check your camera to email daily and report to school in proper CIA uniform. Make sure your outwear is solid white, black, or red. Also, please wear your student ID badge around your neck at all times. Attendance will be issued to the students who do not adhere to the uniform policy. Please remember that you must wear your student ID every day. If you lost your ID, the cost for replacement is $5. If you receive a replacement ID, you must pay for it on OSP. Students who have unpaid balances will not be allowed to participate in field trips. Yearbooks are on sale now. They're $50 until October 31st. The price will rise afterwards. Buy a yearbook now to get a spot at the end of your signing party. Go to www.yearbookcenter.com for our numbers 21027.
Dimensional analysis is a tool.
Attention students, please turn in your Title I service ASAP. You may drop it off at the main
Required
office. If you
to use
misplace your
tool
form,
and use
you
an
can pick it up from
alternative
everyone in the mail.
strategy. Is the way I'm going
Attention
to word
students,
it very
United Way Week
carefully.
starts on Monday with Jersey Day for $1. Sleeveless jerseys must have an undershirt. Help CIE meet
So
the
if
United
you
Way
like
goal.
it, you use it. And if you
Attention
hate it,
seniors.
you use an
If you're
alternative
interested in applying for Silver Knight, Ms. Fleischer will be having a meeting during lunch on Thursday, October 12th at room 34. Attention students. Ibali will be at CIE on Friday, October 13th. They will be selling uniforms during lunch. Cash or credit will be accepted. Please visit www.ibali.com.
And you've got
Or
labs in this
please
unit. This is
select
just
Center
lesson
for
one.
Center for International Education of the Uniform.
And most of this is not even
This
at the
concludes
eighth level.
your
Most of what you learn here is at the
for
pre.
CIE.
Like most of what you learned here today was not at the eighth level. I don't even know if I could say barely one thing you learned today was at the eighth level, maybe just the definitions.
Yeah.
All of this is at the high school 10 level. In the level, this is unit 1, lesson 1. Later on in this unit, it will get more complicated. Before we go for the day, what would you do if you had to calculate the grams? This is the last slide. If moles equals grams over molar mass, and you just memorize this formula, how would you solve for grams? Remember, mass is grams in this class. If they say mass, it's the same thing as grams. Go ahead. Exactly. So it would just be moles times MR equals grams. Let's just work through that for at least one of these. Just so you've got the strategy because it is going to be in your homework. What's the molar mass for CO2? Carbon is 12. Oxygen is 44. Am I okay with you just doing this instead of writing out a chart? Yes, please. Don't write stuff. You don't have to. There's more complicated stuff coming later. 44 is my molar mass. How many moles I got? So 20 times? And how many grams would that be? Alright, so we see the strategy, we understand what to do, it's the same for all of these, just different. All of them are asking for grams, so these last two, just do the same strategy for these final two. It is almost 2:20, so obviously we're gonna stop here. All the homework is not Cambridge questions, it's already been posted, it's on quizzes. You need an 80% on each problem set within 3 attempts, and I'll put 100% in the grade book as assignment grades. So this is an intro. Next class is going to be weird. I'll let you know at the beginning of class how it's going to go. And then we'll continue from there. Yes. Go ahead. Oh, no. Don't worry about I messaged the treasurer. There's a few students I'm sure that this applies to. You're not going to be fine. Oh, are you gonna be? You're gonna. I'm gonna reach out to the treasurer. Don't go home and stress this week. Don't go home and stress this weekend. I reached out to the treasurer. I'll let you know what she said. What? No, you just wow. You're just gonna rub it in. No. I'm sure there's a lot of students in the previous class that messed up. So I reached out already to see if they can open up OST. At the end of 12th grade, if you don't pay it, that can happen. I'll stop at 12th grade. We'll have a chance to again, it's not over for you. So don't stress this weekend. No stress. Your life is not over. Right now. Everything is okay. It's okay. That's cool. You figure out what the if they'll reopen It's actually so much easier to do.
Because I've done so much of that.
I'm sure you have.
Yeah,
So for you, if you're just used to doing it the way, it's a little bit of the way that you're doing it. But if you're not doing it the way already, you only have to do a certain section. All right, have a wonderful weekend, everyone. Don't forget the homework.